I'm a computer science major at UNC Chapel Hill currently, and this is just something I'm very, very interested in. In addition to that, a lot of my hobbies, I just enjoy programming in general and computers and electronics. So for that reason, the Arduino has been a lot of fun. It's actually a lot of fun. There's a lot you can do with an Arduino, and there's a really the limit is your imagination. So as we go through this for the next few weeks, you'll be learning more and more about what the Arduino can do, how it works, and everything like that, and sort of a lot of it's interesting little foibles and surprises and difficulties, and at the same time, all the things that it can do. Now, I've done this presentation a few times. This set of presentations. So this is something I'm very familiar with, but I'm human. I'll make a mistake here and there. If you have any questions or if you want to, mention that I screwed up on anything or anything like that, feel free. You can use the chat box. That's just something I tend to prefer to do. I know Mr. Dubik is a little bit different about that, but that's something I prefer to do because then it pops up in the corner, and then we can just go ahead and address it. I can read it off to everybody, and they may answer and everything like that. That way we can keep the lesson flowing and move through everything, and it just that's the way I like to operate. Plus, it gives you time to think about your question and type it out and everything like that, and make sure that you've got it all set to go. Now, just a quick comment on sort of the structure of how these classes tend to go. At least when I'm teaching it. I believe Mr. Dubik will have some classes with you guys. He'll be teaching it as well. But this is how I tend to operate. We go through the entire lesson, or spend an hour working on the lesson, 50 minutes roughly, and then usually for the last 5 to 10 minutes, we spend time doing question and answer, and also I ask you guys the poll questions. The poll questions are just general questions about the flow of the class and how the content was and how it was delivered to you, whether that was helpful, you guys found it useful and good knowledge, or if you were confused and I just kind of went too fast, or I was too slow and it was super boring, or things like that, so that we can sort of hone in and address those concerns and make it as useful and helpful and enjoyable as possible for you guys, because that's really what we want to do. We want to make it so that you guys sort of get an interest in doing this kind of stuff. If it is, if we do the best we can, and you find that you don't really enjoy Arduino, that's fine. Nobody's making you. But hopefully, if you do find that this is something interesting, we can sort of give you guys the tools and the interest to gain and retain more knowledge on your own. Anyway, that's the plan. But as it stands right now, we've got today's lesson to get through. And like Mr. Dubik was saying in the beginning, this is the build and blink lesson, which is basically one of the simplest things you can do with an Arduino, which is perfect because obviously you want to get started off doing something simple so that you can get more used to it and comfortable and familiar, and you don't want to be introduced to a million tools all at once because that gets overwhelming. So it's referred to as the hello world of Arduino programming, because hello world is generally, if you're learning a new programming language, that's the first program you create, is something that just prints out onto the screen or beeps out or whatever, hello world. It started, I believe, back in the day with BASIC, maybe? I don't know. Could be. But and it might actually be C. But at any rate, it's become sort of a standard for new programming languages. It's become a way to see how a particular programming language might look or flow, and how the syntax might look and things like that. It's a good way to get your feet wet in a new language. Anyway, for today, we're going to answer 3 main questions. What is Arduino? What can we do with it? And how do we control it? We're going to be spending a lot of time on the last question there. That's actually the bulk of this presentation. But the first 2 we do at least touch on in the beginning. So, what is Arduino? Hello, there we go. Arduinos are microcontrollers. They are open source microcontrollers, well, insofar as the programming is concerned. That may not mean anything to you, so let me explain a little bit further. Factories, right? Factories have to be controlled by something. You know, back in the day, you can imagine like a dude just like pulling levers all over the place and stuff like that, and you see that kind of stuff in old cartoons. But then the automated factory was obviously a big boon to commercial development and everything like that, which meant that you no longer needed people to control at least some aspects of the assembly line. However, you need something to control them. If not people, then computers. Enter essentially what's known as the programmable logic controller. I mean, that came later on. Factories were controlled generally by other things. But certainly modern factories are controlled by PLCs, or programmable logic controllers. And basically what those are is they're computers with a very specialized programming language. Yeah, I can do that. Certainly. I was just asked to make it more like a slideshow, so let me go ahead and there we go. Does that make it easier for you? Well, all right, excellent. Good, good. Okay, so yes, programmable logic controllers. They're sort of computers with specialized programming languages. They don't have like they're not like computers that we traditionally think of where they have like operating systems and stuff like that. You know, your computer has either Windows or Mac or Linux, some flavor of Linux, and you've got like a mouse and a keyboard, and you can plug stuff into it, and play games on it, and it outputs sound from YouTube videos and stuff like that. They're not like computers in that sense. Basically, they're very simplified machines. You write some code, you upload the code to them, and they execute that code forever and ever and ever until you remove power from them. They don't generally come with monitors. You can't play YouTube on them. They don't have operating systems. They're just very, very stripped down computers that run their specific code that you've given them, always and without fail, ideally. Now, the strength in this comes into the fact that they can be hooked up to electronics. They can be hooked up to big giant machines. They can be hooked up to these huge power distributors to send information to other things. They can be hooked up to these giant temperature sensors that provide information for them, and then they can take all this information in and process it and send out output along appropriate lines so that the factory continues to run smoothly, and it shuts down in case it gets too hot or it fills with water or whatever, stuff like that. But that's been basically the backbone of factory control. Microcontroller is very similar to a PLC. It's just very small. It's micro. It's tiny. Hence microcontroller. So it's going to be a stripped-down computer. It's going to have a specialized programming language. And as you can see, it's going to have these weird pins on it, which if you've ever messed around with like a breadboard or something like that, you can take pins like those and either take an input from buttons and switches and sensors and things like that, and then send them out to lights and motors and stuff like that. So you can have a very customizable sort of set of electronics that can be automated for whatever you need. I say whatever you need, it sounds very vague, and that's because there's a lot you can do with these. In fact, they're useful for things like CNC or 3D printers, which are just basically, this is a 3D printer, fabrication machines, quadcopters. You can use an Arduino to control the motors in the quadcopter and take in, input from like an RF transceiver. You can set it up to be just like a light show in your living room that listens to the sound that's playing through the sound system and changes the color of the LEDs lighting up the water and the level of the water to match the beat and the tone of the music. You can set it up so that it's it's hooked up to something that takes like a signal from your phone and is hooked up to a servo that locks your door, so you can lock your door when you're out of your house and unlock your door remotely. Really with things like Arduinos, there are very few limitations. Oftentimes, our imagination, our access to materials is the limit, honestly. But yeah, so let's spend some time going over the hardware of the Arduino, some of the electronics for this project, the Arduino software, and then just getting a blinking LED working. Let me set up an alarm. I no longer have the ability to see what time it is momentarily. Okay, I'll just go ahead and do that. All right, so yes. Now, this is new for 2017, motors and transistors. May not mean much now, but these are interesting things. Motors are cool because they are going to be the legs and arms of your Arduino. Transistors are cool because they're going to be... Okay, let me put it this way. Your computer operates on tons and tons and tons and tons and tons and tons and tons of transistors. Transistors are very useful for intelligently distributing power in electronics. In fact, the Arduino is made up of tons and tons and tons of transistors. Not as many as your computer, but same principle. You can do a lot of interesting sort of logic stuff with transistors and electricity. So transistors are pretty cool, and hopefully we'll get the ability to see why that's pretty cool. So the intro to the Arduino hardware. Now this is all of the stuff in the SparkFun Inventors Kit. Not everybody's going to have this, obviously, but this is just the stuff that comes in the kit. If you end up getting it, excellent. If you don't sweat it. All this stuff is going to be in circuits.io, the simulation software. So you'll be able to use it as if you had it, right there in front of you. Granted, it's not going to be physical, but same difference. So it comes with jumper wires, which are useful for breadboards. It comes with LEDs, which are useful for light. It comes with photoresistors, which are useful for detecting how much light there is, and we'll see those too. The piezo element is basically a speaker. You've got two different types of resistors, which basically the little strange symbol there is for ohm, which is how much it resists. So we've got a 330 ohm resistor, and then you've got a 10,000 ohm resistor. Obviously, the 10,000 ohm resistor is going to resist more than 330 ohms. And we'll get into why that's useful and important and sort of the differences and everything like that in the subsequent lessons when we go over them. You got a temperature sensor, get a transistor, get a potentiometer, which is basically just a resistor that you can turn a knob in order to change its resistance. You get a diode, which is kind of like a one-way street for electricity. In fact, LED, light emitting diode, it's just a diode that puts out light when electricity goes through it. You got a DC motor, which is a direct current motor. So there's a motor in there. You got a push button. It's a button. It does button stuff. You got the breadboard itself and a breadboard, which will allow you to hook the breadboard up to electronics and create more complex circuits and things like that. You got a flex sensor, which will detect when you've bent it. Soft potentiometer, which is like this resistor with a knob, but it's just like a strip. You got a servo, which is a specialized type of motor. An IC, which is like a smart, it's an integrated circuit. It's a chip. A relay, which will allow you to relay electricity, and an LCD screen. Again, if you don't have it, this information is a bit superfluous, but it's kind of good to know all the stuff you can mess with. Now, as far as the hardware on the Arduino itself, as opposed to all the peripheral stuff around it, you've got the power jack, which can take in anywhere from 7 to 15 volts. Yes, actually, we're going to, once we go through all the hardware and stuff like that, I'll spend time introducing circuits.io to you. It used to be called 123D Circuits. It's contained entirely within the browser. You don't have to download anything, and you can hook up, like there's a little Arduino component that you can hook up other stuff to. You can create these circuits with the breadboards and everything like that, just like you would in a physical sense. And then you can also program the Arduino. You can put um, uh, code into it in order to make that Arduino operate like a real physical Arduino would. It's a very handy thing. So you got the power jack, you've got the USB. Everybody's familiar with USB. Everybody's familiar with power jack. It's just a standard barrel plug, but everybody knows USB. It's what your keyboard uses to plug into your computer or your mouse. You've got power pins. Power pins take in power from another circuit, or you can use the Arduino to power a circuit. So there's that. You've got the analog pins and the digital pins. Now, these are referred to as GPIO pins, the analog pins and the digital pins. GPIO just basically stands for General Purpose Input and Output. That means that these pins can be used either as input pins or as output pins. Let me see here. So you can set them up so that the Arduino sends information out or it receives information on those pins. And then the jumper wires that are used for like the breadboard and stuff like that would plug into these pins. So it's literally just like a bit of copper. But yes, the reason why we distinguish between analog and digital pins is because that's a very important distinction to make in the electronics world. Analog and digital are two very different things. Basically, we'll get into more detail on this later on, but the difference can essentially be boiled down to digital can only send either an on or an off signal. It can only send or accept either an on or an off signal, 1 or 0, just like binary, right? Or just like if you look at a power switch that's got that little let me just go ahead and draw this symbol. It's got like this kind of a thing. That's actually the 1 and the 0 combined. That's the generic power symbol though, but that represents the on and the off. So yes, a digital signal will accept or send either just on or off, only 2 signals. Analog, however, can send, technically speaking, an infinite number of values from full on to full off. So in our example here, if the Arduino might send out 5 volts, a digital signal could either send out 0 volts or it could send out 5 volts. An analog signal, though, could send out 0 volts, it could send out 0.1 volts, it could send out 2.2 volts, it could send out 4.9 volts, it could send out 5 volts. You know, it could send out any value from 0 to 5 and all in between. And the reason why it's infinite is because you can send out 4.9 volts or 4.99 or 4.999 or 4.99999. It's, you know, it's sort of a mathematical trick in essence. But yes, we'll get into more detail on that. So if that didn't really make any sense right now, or if it was something that was kind of like, oh, okay, it didn't really seem useful, that's okay. It will make more sense, and you'll see why it could be useful later on. I just want to let you guys know now that this exists. All right, so yeah, analog pins and digital pins. It's also got a reset button in case you're trying to like make the Arduino code run from the beginning again. Maybe you're trying to debug something that's happening in the beginning and it only runs through it once before it starts going into its regular code. You can always just hit the reset button and bring it back to square one. Then you've got a couple of LEDs on it, which are very useful. You've got the transmission LED, the TX LED, which signifies that the Arduino is sending information out on the USB. You've got the RX LED, which is the receiving LED, which tells you that it's receiving information on the USB. You got the pin 13 LED, which basically lets you know whenever you're either sending or receiving a signal on pin 13. Now, why might that be useful, you might ask? Well, it's good for debugging purposes. You can set up a whole circuit, and then it could be this big complex circuit, and you start it up and it doesn't work. Well, you can use the pin 13 LED to see if you're actually sending power out from the Arduino at the appropriate times. If you are and it's still not working, then something's going on in your circuit. If it's not, then something's going on in your Arduino. It's just that kind of stuff. And then you got the power on LED. If it's on, your Arduino is on. If it's off, it's not on. Pretty self-explanatory. We'll go ahead and skip that for now. So let's review electronics a little bit as well. So I've been mentioning the breadboard and stuff like that, but I haven't really explained what it is. A breadboard is a very, very useful and easy way to prototype circuits. Basically hook up these big complex circuits and see if they work or not without having to worry about soldering or circuit boards or anything like that. They're very useful for that because they don't, as the name implies, solderless breadboards, they don't require any soldering, which is melting conductive metal to a circuit to, to add a component to a circuit board. All those little droplets of metal, if you look at like a motherboard or like a circuit board or anything like that, that hold those components in place, that's solder. And it's meant to keep that component in place, but again, it's conductive, so it can be added to so it is added to the circuit. Solderless breadboard, you simply plug a component in to the breadboard. It's just got these rails, these little metal conductive rails that you literally just press a component into, give it a little bit of force, and it gets connected to the rail, and then everything on the rail is also connected to it. That means that breadboards have sort of a strange way that, everything's connected. They're referred to as buses. Buses are essentially, pins that are all connected. So if you want to connect a resistor to an LED, you don't need to plug them into the same slots. You can actually plug them into the same bus, and so electricity will be transmitted from one to the other. Like again, if we're going to take this under the hood look at the breadboard, you've got this set of slots here that are all connected to one another. So we could plug in an LED here, and we could plug in a resistor here, and they would be connected to one another, which is kind of useful for making a complete circuit. But it's important to note what is connected on the breadboard. Like, what are buses? Where are the buses? Now, in the middle, they're all horizontal buses. That is to say, they're all connected horizontally. Not through this middle area, mind you. This big plastic break here breaks the bus. So this side is not connected to this side. On the other hand, on the right and left-hand sides here, these are vertical buses, and they're connected all the way along the length of the breadboard. So from top to bottom. And these are generally very useful for hooking up your power for the circuit. And you'll see why as we get more complex circuits hooked up. But yes, that's something important to note for breadboards is in the middle you've got horizontal buses, so everything on the same row on either side of the plastic is connected. And on the sides, you've got vertical buses, and those run from the top to the bottom. So everything on the same column is connected on the sides. But yes, so there you go. But that makes it, solderless breadboards are very useful for being able to hook up big circuits very quickly in order to test out whether or not they're going to work or anything like that. So yeah, here's actually a better diagram than what I drew haphazardly. As you can see, each solid color, whether it's red or blue or gray, is an individual bus, so a set of slots that are all connected to one another. So as you can see on the edges here, the red and the blue are all connected along the entire length. These have little symbols for them for power and ground on most breadboards, and they're generally referred to as the power and ground rail, or the hot rail and the ground rail. And that's generally their specific purpose is to provide power for the entire circuit or to provide a ground for the entire circuit. And then you got the horizontal rows. 5 horizontal sockets. Components placed in the same row will be connected when in a circuit when power is running. Those are for building the rest of your circuit, separate from the power and ground rails. This is actually a picture from 123D Circuit, or circuits.io now. which is pretty helpful. Now, this means that components need to be placed in a very specific way when they're connected to the breadboard, because it's not generally a good idea to connect a component to itself, because bad things happen there. And we'll see here. So these are okay, right? As you can see, since these buses run horizontally and these buses run vertically, this resistor here is jumping from one bus to another bus. And one of its sides is on the same bus as the LED. And then the LED, runs out a separate bus, which goes to power and ground and all that stuff. This one's also fine, even though they're not connected to one another. But the resistor is on two separate buses, and the LED is on two separate buses. As you can see up here, this is the same deal here as well. This is not okay. The resistor is connected all along the same bus. Same with the LED. This is bad. And that's because electricity is lazy. It travels the path of least resistance. This is meant in a literal sense as well. So, well, it's always meant in a literal sense. So if you have a piece of bare wire and you have a resistor, well, a resistor's job is to resist. Look at that resistor. It looks like a loaf of bread with a stick. A resistor's job is to resist. That is to say, it increases the resistance for electricity to travel down. So if electricity has a choice for two paths, you can either travel down the resistor or it can travel down the bare wire. Because the resistor provides more resistance, the electricity will go down the bare wire, always and forever. Any component, in fact, is going to have some small amount of resistance to it. Wire itself has some small amount of resistance to it, but any component will have that. A diode, an LED, a potentiometer, all these things are going to have some form of resistance to them. So if you place something on the same bus and then you hook it up to the circuit, you're going to run into a situation where the electricity is going to travel through the wire. It's going to prefer to travel through the wire instead of through your resistor or your LED or whatever. This is referred to as a short circuit because it is, well, it can be referred to as a short circuit because it's going not in a direction that you want it to go. Generally, short circuits are circuits that are actually shorter than you intend them to be, like it's skipping half of your circuit and then going back to the beginning, which can also be bad, but it can also be very bad. But this is basically a form of it as well because it's skipping something that provides resistance. This can be especially bad when it's skipping a vital resistor, because the purpose of a resistor is to reduce the not really, but basically the amount of electricity going through a given component. Specifically because some components can only take a certain amount of electricity, a certain voltage, a certain amount of amps, things like that. If a component is receiving too much power, in the middle component, so in the middle example is the LED still connected to the resistor. So this one right here. Are you referring to this bottom one or this top one? Bottom one. In this bottom one, they are not. They are not actually connected to one another, and that's an excellent question, because as you can see, this LED is hooked up to these two buses here, and this resistor is hooked up to these two buses here. Well, maybe, I don't know. It might be pretty difficult to see after it's been buffered through the internet and then placed on a window that's smaller than my screen. But yeah, these two components are on two separate buses, so they are not connected to one another because there is nothing that is bridging that connection. So like there's no wire that runs from like here to here, bridging the connection between the two. So yes, because they're on two separate buses, they are not connected to one another. Thank you for asking that, actually. But yeah, so short circuits are bad because you can make things explode, in essence. If you got too much power going through something, you can cause a component to catch fire or literally pop in more dramatic examples. And both things are bad. They can be kind of fun when they happen, but then you remember that you have to replace a component. And it could also hurt you, which is very bad. But yeah, there is a phrase, because a lot of times when components start to burn or explode, they release smoke. And the joke is always that you let the magic smoke out of the component, now it will no longer work. There's every component is filled with some magic smoke that makes it work, and as soon as you pop a component, you open it up and let the magic smoke out. Now it'll no longer work anymore. So yeah, don't let the magic smoke out. But yeah, so that's sort of how to hook something up on a breadboard. Now, as far as LEDs are concerned, like I said, it's a light-emitting diode, so it is a diode, a one-way street for electricity, that also happens to give off some light. Now, the important thing to note is, how do you tell electricity which way is the way you want it to go? If it's a one-way street, imagine like you're building a road just out of whole sections of road, and you want to put down a one-way street at some point, like just in a strip of road. How do you say which way is the correct way? Well, obviously you have to orient the street properly, right? You have to make sure that the street's pointing in the direction that you want the traffic to flow in. This is a terrible example. I apologize. I'm sure this will be much better when I'm no longer sick. But the LEDs, diodes in general, work off a principle of they have polarity. There is a right way and a wrong way to insert them into a circuit. The wrong way is so that the one-way street is facing in the direction opposite to everything else in your circuit. The right way is so that the one-way street is facing in the correct direction. But it is important to note that it is important how you plug in an LED. It's unfortunate and it's kind of annoying, but regardless, you always want to make sure that you're mindful of the two legs on an LED. If you had a physical LED, like, in your possession, and you looked at it, you would notice that one leg is going to be longer than the other leg. On a lot of LEDs as well, at the top, there's some side that has like a notch taken out of it, almost like a bite taken out of it. These are how manufacturers let you know which leg is which, because again, it's important. Anode and cathode. You have to make sure that you plug the anode into the like the beginning of the circuit, and the cathode. Basically, electricity flows from the anode to the cathode. Let's just put it like that. Always and forever. So you got to make sure you hook the anode up at the beginning, or towards the beginning, and the cathode up towards the end, facing towards the end of your circuit. Otherwise, electricity is going to either be flowing the wrong way or it won't be flowing at all. If you look at that LED, the longer leg will be the anode and the shorter leg will be the cathode. If you look at the top of the LED, the place where the bite's taken out of is going to be the cathode. But yeah, it is important to note how LEDs are plugged in. It is important to plug in LEDs in a specific way. Just keep track of the fact that the anode is where electricity enters the LED, and then the cathode is where the electricity leaves the LED. Resistors, however, they don't care. You can plug in resistors any which way, forwards or backwards. In fact, that doesn't even really exist for a resistor because they really don't care. Resistors are non-polar. Unlike LEDs, resistors don't care. Resistors block the current too. Basically, the reason why they don't care is just because they turn electrical energy into heat energy. That's all they do. They just sit there and then they get hotter. obviously to a certain point. They don't become like scalding boiling hot unless something's seriously wrong with your circuit, or you're putting through way too much power and you've got this massive resistor on it. But they will exchange electrical energy for heat energy in the interest of blocking some of the current in a circuit. Also, the important thing to note is, like I said, resistors have different resistance values, basically how much they can resist, and you need to know what you're resisting, how much you're resisting, because if you put on a resistor that's too strong, it's going to prevent your components from getting enough electricity. If you put on a resistor that's too weak, it's going to make your components pop and let out their magic smoke. So resistors are nearly always, unless they're very big, and even then they'll still follow convention a lot of the time, but nearly always the resistance value is indicated by a set of bands that are actually painted onto the resistor, and the color of those bands tell you. So in this case, it's orange, orange, brown, and gold. This is just from a purely academic point of view. There are a lot of things that you can look it up on Google and stuff like that, the different band colors and what they represent. But just, I'll tell you guys right now, basically the way you read the bands is the first band is the first significant digit, the second band is the second significant digit, and the third band is what power of 10 you multiply these first two by. And then this last one is the tolerance, basically. Manufacturing weirdnesses and impurities and things like that mean that if a 330 ohm resistor is manufactured, in reality, it might resist 325 ohms or 335 ohms. Like it might be in reality a 331 ohm resistor, even though it's listed as a 330 ohm resistor. That final band, it's either going to be gold or silver, not there at all. Basically denotes the tolerance. So I believe gold is plus or minus 5%, which means that a 330 ohm resistor, you're guaranteed that it's not going to resist less than like 338.5 ohms or more than 331.5 ohms. Because 10, oh, no, wait, wow, math is bad. 1% of 330 ohms is 3.3. So there you go. So it would be larger than that. Anyway, that would be 0.5%, which would be incredible. Excuse me. But anyway, that's how you read that. We can get more into that later when we go over resistors and stuff like that. And also, there are plenty of tools now which assist you in that. It's becoming a thing that's less common to know those by heart, but it's still kind of a neat thing to know. So whatever. Anyway, our blinking light will be basically a very simple circuit. We'll have a power source, we'll have an LED, and we'll have a resistor, and that's it. I'm actually going to take this opportunity to go over 123D circuits, which is actually not referred to as 123D circuits anymore. It's going to be circuits.io. So let me go ahead and just, if you type in circuits.io, let me go ahead and put this into the chat box as well, into your browser of choice. I think it actually has to be Chrome in order for it to work properly. But they might have updated it since then, so not necessarily your browser of choice. But yeah, circuits.io, hit enter, and you'll be taken here, Autodesk circuits. And there's a lot going on here. I mean, it's obviously advertising everything and all that good stuff. No, it doesn't matter. Resistors really don't care. Like you can plug it in either way because literally its only job is to turn electricity into heat. And so it really doesn't matter which way that electricity goes. It just does its job and lets it right on through. Resistors are very easy, They're very, very easy going. Well, if it's relative to another component, that just depends on the circuit. Um, for most things, it's not going to matter. There's a strange quality of electricity where you could put a resistor after the LED and it would still be okay, but not all the time. Electrical engineering can be wonky sometimes. Um, yeah, as you can see in this example here. Now, this is going to get into another concept that it's kind of strange, but essentially, electrons flow differently than we model, but it still works. Insofar as the direction that they go is concerned. It's very strange, but electrical engineers didn't figure it out until they'd already created all these models, and they went, well, it still works anyway, so we'll just keep it, I guess. So models don't exactly jive with how reality works, but then they do because it still works. Electricity is really weird. Anyway, circuits.io. This is where basically all the magic's going to happen for the next couple of weeks. This is where we're going to build our circuits and program our Arduino and run it and see how it works and see if it works and figure out what's going wrong with it and all this kind of stuff. It's actually a very easy to use and worthwhile program. It's very good to simulate well, circuits without having the components before you want to spend money on buying the components. In case you're concerned that the components are going to catch fire, you can also, turn them into printed circuit boards, which you can then, if you're confident in your circuit, you can turn it into a printed circuit board, which can then get printed for you by an outside service for a decent price. And I say decent as in not necessarily cheap, and sent to you and everything like that. But most importantly for us right now, it simulates an Arduino and all of its components that we hook it up to. So what we're interested in up here is the sign up for free button. Just go ahead and click on that, and you'll put in, your country and your date of birth, and I believe you need to be 13. Let me see here. March 1st, let's say 2003, because that would be 13, not yet 14. Right, next. And I believe that should work. It's either 13 or 16 is the cutoff. But regardless, if it is the cutoff, what it essentially means is let's try 2012. Yeah. Okay. Username, password, and your parents' email. If you get your parents' email there, means that you're less than 13, and your parents will have to basically sign off on your account. But you guys are in high school, so that shouldn't be an issue, even remotely, unless you're super duper smart and precocious. Anyway, I'm getting sidetracked. Click the sign up, put in your birthday, put in your, a username and a password that you can use, because you'll need to sign in with it. Like so. Once you do, though, well, you might need to go through like an authorization or authentication process. They've changed it a couple of times, and it always changes in between classes. They're actually bringing some pretty rapid iterations to this. So that's why I sound so uncertain about what the process is, because this was not Autodesk circuits when I first started teaching this. This was something entirely separate, and I had a different. Oh, you don't have to? Excellent. Thank you very much. Thank you. Great. So you don't have to verify or anything like that. But yeah, I actually had a different login when I first started using this. Anyway, I get taken to something that might look like this. it might look like this. Who knows? You know, but this is going to be basically your desktop from which you can start new projects or edit existing ones or something like that. Anything like that. As you can see, the last time I used this was November 10th of last year because we did an Arduino set of presentations then. But what I'm going to do is I'm going to go ahead and click on Create here. As you can see, we've got a whole bunch of different stuff here. By a whole bunch, I mean 3. It's hard to count that high for me, so I just say a whole bunch. We got the electronics lab, we got PCB design and manufacturing, and we got the circuit scribe. We're not actually, as far as I know, yeah, we're going to be using the electronics lab. I don't think we're actually going to touch the PCB design or the circuit scribe. We're just going to be using the electronics lab because that has all of the features that we need. And as you can see, we get taken to a very similar page, except there's a new button here at the top and also designs down here from the electronics lab, but this one says New Electronics Lab. Just go ahead and click on that. And we get a little loading bit. My poor internet. There we go. Once a breadboard appears, bam, it's fully loaded. Now, it comes with the breadboard by default. That's perfect. That's exactly what we want because this is our virtual breadboard for our circuits. In addition, we can also, if we were so inclined, add an Arduino. I know I'm not going over how to add it right now. That's okay. We're actually going to go into detail about how to hook it up in the next lesson. But I just want to show you guys, yes, there is a virtual Arduino here that you can use. We can draw circuits. We can add components to it, like an LED if we were so inclined. And, you know, a resistor, and plug all this stuff up together, and we would have ourselves a neat little circuit that we could then simulate. So yes, if you do not have a physical Arduino, don't sweat it. You've got a means to an end right here, and it's pretty cool. But as it stands right now, I want to make sure that we get the at least the poll questions and the initial question and answer time sort of addressed and out of the way, because question and answer time the first time can either go one of two ways. You can either you have no questions or you have a billion questions. So I want to make sure that I give you guys enough time for that anyway. So let me go ahead and ask you guys the poll questions. Once I'm done with that, we'll do question and answer time. If you have any questions, go ahead and throw them into the question box, and then I'll get through them in order. If you don't, you're more than welcome to head out. Have a wonderful couple of days, and we'll see you on Thursday. Again, that's after we do the poll questions. But here we go. First poll question incoming.